Hello everyone, apparently it's cold today and so my kids don't have school, so I'm not going to be in class, and so we're filming this live, alright? So in your notes packet, thank you, I'll be here the rest of the week. Okay, if you look at your notes packet, you should find example 2 in your notes packet, which is about the International Space Station orbiting the Earth and stuff. Okay, so the kinds of questions that you're going to have in tonight's homework are going to include all the things that you saw in last night's homework about like gravitational forces and stuff, but it's also going to start asking questions like, how fast does this thing that's in orbit go around whatever it's orbiting around? So we could ask about like the Earth going around the sun, we could ask about a satellite going around the Earth, we could ask about a satellite going around Jupiter or something. So it doesn't really matter what you're talking about. It's the same process for all those kinds of questions. All right, so in example 2, it says we've got the International Space Station. It says it orbits the Earth at a distance of 370 kilometers above the Earth's surface. And then part A just wants to know, it's like a simple geometry question, what is the radius of its orbit? Okay, the reason it's asking this question is because, if you recall, in all of the formulas that we've got in this unit, there's this r squared thing. So somebody remind me, where do we measure r from?
Center to center.
Center to center, okay? So we're not going to plug in 370 for r. Number one, that number's in kilometers, so that's extra wrong. What would we need to convert that to? Meters, okay. So this is 370,000 meters. Okay, so that's like the number one deception that will be played upon you in this unit, is they'll be like, kilometers. Just kind of quietly slip in that wrong unit, and then you have to know to convert that to meters. All right, the second deception is the fact that they gave you an altitude instead of the center-to-center distance that you actually needed. So it's very often going to be the case for satellite problems that it's going to be r equals big R plus h. Okay, so when you see the little r, I'm always going to use that to mean center-to-center distance for these questions. If you see big R, that's always going to represent something like the radius of a planet, or whatever it may happen to be. All right, everybody good with that? Okay, all right. So if we calculate the actual center-to-center distance, we're going to have to throw in the radius of the Earth, which is, I won't make you convert this for the sake of saving time on YouTube. Okay. 6,400,000 meters plus through, so 6,770,000, a lot of meters. All right, and so that right there is the orbital radius for the Earth's orbit around, or sorry, for the International Space Station's orbit around the Earth. Okay, everybody fine with that one? They're really excited. Really excited. We don't know what's happening. Okay, part B now wants to know the force of gravity on the International Space Station. I'm going to skip over the calculation for this just for the sake of brevity. But if you did want to calculate it, what formula would you be using to calculate the force of gravity on it? That's the one. Okay, so this is just a matter of like plugging in the numbers, right? You plug in this distance, you plug in the mass of the Earth, you plug in your universal gravitational constant of 6.67 times 10 to the negative 11th, and then you'd have to plug in the mass of the International Space Station, which is given to you. Okay, now part C of this question wants to know the force that the International Space Station exerts on the Earth. What should we say for that one? Looks like that's a lot of radio silence for YouTube. YouTube listeners have tuned out by now. Okay, guys, if I calculate the force that the Earth exerts on the International Space Station, I would be using G, Earth, ISS, distance between them. If I wanted to calculate the force that the ISS exerts on the Earth, would I be using any different numbers? No. So that means the two forces they're the same. This is an action-reaction pair, which is the answer to D. Okay? It says, how should we classify these forces? It's an action-reaction pair. Anytime you can say those two objects exert the same force on each other, odds are pretty good it's going to be an action-reaction pair. And in this case, it has to be because the ISS pulls the Earth this way a little bit, and the Earth pulls the ISS that way a little bit. Okay. Everybody good there? Okay, all right. So most of this was not new. This is review from what we talked about previously, but we had to talk about it to get to part E. So skipping down the page a little bit. It's asking about the strength of the Earth's gravitational field. Well, there's a formula we've never seen before. Gravitational field. The formula for that is pretty similar to the equation for force. It's that right there. So what is the difference between these two formulas? Just one M. So if we're asking, like, what's the Earth's gravitational field up where the ISS is, we're only really using the mass of the Earth to calculate that. Synonyms for gravitational field are acceleration due to gravity. Pretty much that. Okay, so let me write it down. So this is gravitational field. That's what the G with an arrow over it stands for. And it means the same thing as acceleration due to gravity. Okay, so what if I plugged in the mass of the Earth and the radius of the Earth? Anybody want to hazard a guess as to what number that equation would spit out? It's acceleration due to gravity. So if I plug in the mass of the Earth and the radius of the Earth, what should I get? Maybe we'll pause the video for a moment and then you guys can plug it in and calculate it. Let's do that. All right, so a little calculation just to see what would happen. Plugging in the mass of the Earth and the radius of the Earth. Using these slightly rounded numbers, I get 9.77, which is about 9.8. If I use slightly more precise values, I would have gotten just about exactly 9.81, which is the acceleration due to gravity at the surface of the Earth. So you shouldn't actually be surprised that this number for acceleration due to gravity comes out to 9.8 because that's the acceleration due to gravity at the surface of the Earth. All right, this number right here is called surface acceleration. All right, which is the gravitational field at the surface of an object, or the acceleration due to gravity at the surface of an object. All right, what are the units for it? No, that's a horse. What's acceleration measured in? All right, meters per second squared. Because that's what a gravitational field tells you is acceleration. Okay, so meters per second squared. Now, part E wanted to know what the acceleration due to gravity up where the ISS is. Let's make a prediction. Is it larger or smaller than 9.8?
Small.
Got to be smaller, right? If you are further away, then it's got to be less than 9.8. All right, is it going to be 0? No. Is it going to be close to 0? Probably not. That's a good guess. I mean, usually people imagine that it is going to be like basically zero because they know that astronauts are weightless in space. But if you recall, the real reason why they appear to be weightless is just because the ISS and them and everything on it are constantly actually falling towards the Earth. They're just going sideways fast enough to keep missing it. Okay, so since they're in constant free fall, it's like they're weightless. But actually, the field is nowhere close to zero. Okay, 8.7. Okay, so it's less. All that means is that if the astronauts like stopped moving sideways, like just the ISS stops suddenly, they would fall towards the Earth at a rate of 8.7 meters per second squared. That's what would happen. And then they would crash and burn. But they'd probably burn up in the atmosphere on the way down, but whatever. Okay, now part F wants to know why doesn't the ISS fall if the acceleration is not zero? We already kind of said the short answer is because they're moving sideways really fast, right? If they're moving sideways fast enough, then they keep missing the Earth. So that's probably what you should put there. There's a particular speed that an orbiting object has to be moving at based on where it's orbiting. So depending on the height above the Earth at which you are orbiting the Earth, your speed has to be different. More or less what it ends up turning into is, we'll take two formulas that we've learned before and put them together. What force makes the ISS move in a circle? Okay. Cover this stuff up here. And the thing that provides that force is the force of gravity. So the force of gravity equals the centripetal force that makes the ISS go in a circle. Okay, so from this we can now calculate the orbital speed of the International Space Station. All right, now if you have to do this on the homework or on a test or on a quiz, I do want you to derive this formula that we're going to get here every single time you use it, because I don't like magic formulas. I want you to actually know how to derive it before you actually plug in the numbers and get an answer. Okay, so this is not a difficult thing to derive. Does everybody see that you can just set those two equations equal to each other and then solve for V? Let me pause the video a moment while you solve for V. All right, and that right there is a beautiful equation. What it shows is that the orbital speed really only depends on, the value of g, the mass of the Earth, and the radius at which it's orbiting. All right, the other thing that this shows is that the further out your orbit is, the slower you can go and maintain an orbit. All right, since r is on the bottom, if r is a bigger value, then the value that v would come out to would be smaller. Okay, again, for the sake of saving time on internet videos, if I plug in mass of the Earth and this radius that I got over here for the orbital radius of the International Space Station, I get 7,700 meters per second. All right, that right there is incredibly fast. You don't really probably have a good way to put that in context, meaning you can't probably wrap your head around it. So just for comparison, I gave a question one year on like the speed of a bullet coming out and like using a machine gun to like make a car go forward. So basically it's a rocket engine powered by bullets. Okay, probably not a safe means of transportation, but the speed of the projectile coming out of an M80 machine gun is only 850 meters per second. Only. So this is going way, way, way the hell faster than a speeding bullet. Okay, and I'm basically out of time for this video. Hope you enjoyed it. Okay, thanks, bye.